There are 6 problems in the u09a1 homework assignment that's due this week on Tuesday, so I just thought I would run through a quick demo of some of the key features of the homework. It's not my intention here to show you the actual answers. It's not even my intention to explain all the details. I just want to go through the basics of how to solve this week's homework problems. You can slow down and pause this video to look at different pieces of it as you want, so I just want to go through the 6 problems fairly quickly. The first problem basically has 2 different parts to it, 2 different things we need to know how to do. One is on the left here, taking a z-factor and coming up with the confidence interval that it represents on a two-tailed basis. So for instance, if I have a z alpha of 1.645, how could I turn that into the confidence level that I'm interested in? So typically I'll do 1 minus the norm's dist of that to get a probability in the one tail. So each of the tails is about 5%, which means that the 2 tails together, when I double that number, are roughly 10%. So 1645 will give me roughly a 90% confidence interval. Throw away the extra decimal places as you like. Remember, you've always got to look at the instructions in a homework assignment for how many decimal places you're supposed to enter in your answer. So turning a z-factor into a confidence level is something you want to know how to do. You also want to know how to do the reverse of that. What if you're told what is the confidence interval that I'm looking for, therefore what is the z-factor I should be looking at? It's really, algebraically, it's just the first side in reverse. So 95%, if I subtract that from 1, I get the probability in the 2 tails. I'm doing a 2-tail test under my z-curve, so I want to cut that in half to 0.025, 2.5% in each tail. And if I look up the inverse, the norm's inverse of that, I'll get the 1.96 as I go through. So if I enter the 90 here, I should get the same 164 that I had over here because it's very circular. So just keep in mind that the norm's dist function turns a z into a probability, and the norm's inverse function turns a probability into a z. They're simply the inverse of each other going through. The second problem looks at a set of ranges to try to understand them better. So we're given, for instance, a lower confidence limit and an upper confidence limit. We're given that twice. I think we're asked to come up with what the x-bar would be. So the x-bar is always the middle of the confidence curve. We can calculate that in Excel here by just entering the average. If you want to save time, take the average of the 2 numbers at a confidence interval and you'll know what the x-mean was. You can also calculate the range of values, how far apart are those ranges, to know how wide your confidence limit is. So we have 2 of them here. One is 39.4 wide and one is 35.2 wide. The wider confidence interval always has higher confidence. The wider you cast your net, the more likely you are to find the x-bar that you're looking for. The narrower you're looking for, the narrower range is always the lower confidence interval. So you're not always asked which is higher, which is lower. You might be asked which one is 90%, is likely to be 99%. You can't actually calculate the percentages, but you know that the wider the limits, the wider the confidence range, the higher the confidence that you have. Moving on to another problem, if we're given some data, some proportions data, if you're given 1,000 of something and told the probability of success is 0.75, you can calculate how many you would expect to see as simply NP as you go through. So N times P will give you the expected value as you go through. There's also a formula, the square root of N times P times Q, or where Q is 1 minus P, will give you your standard deviation of the proportions curve. So you can always calculate. So we know what our average is, we know what our proportion is. And then usually you're given the question of what's the likelihood of being less than some value or greater than some value or some in-between range. So in my example here, given this proportion, I'll say what's the probability with my expected value of 750 of actually falling between 720 and 755. So for each one I have to adjust, because I'm not, proportion, I'm dealing with a discrete binomial probability and I'm trying to adjust to use the z, so I've got to subtract the 0.5 from the lower value and add 0.5. That's the continuity correction we learned about in a previous chapter. Those are the actual numbers I'm going to do my probability of. I can then calculate my my z-factor coming through, so it's my F2, which is my expected value x minus the B4, which is the expected value. So it's 719.5 minus 750 over my standard deviation of 13.1. That gives me a z of minus 22. I can then do the norms dist of that to get the probability of it, and because I'm dealing with two tails, I do it twice and add together the numbers and subtract from 1. So the probability of being outside of that range is 1 minus h2 plus h3. If they say what's the probability inside the range, just don't subtract it from 1. So always pay attention to the wording of your problem, because the wording won't necessarily match exactly what I'm showing you here. Moving on, we want to be able to calculate the confidence interval on some range of values. Suppose I have a sample of 40 and an x-bar of 412.8, and I'm told that the standard deviation is 112.1. So I have to be given that, because I wasn't given the raw data as I go through. And they ask, what is the 95% confidence interval of that? So how would I go about that kind of a calculation? I typically calculate my alpha, which is 1 minus the confidence interval. If I'm doing a two-tailed test, I have to take that alpha and divide it by 2. And then I go and look up the z factor. So the norm's inverse of the alpha over 2 gives me a 1.96. You'll quickly come to memorize numbers like 196 and 164 because they're the standard numbers you go with, but it could be anything. So from that, I can then calculate the size of the interval. So it's my B8, so it's my z factor times B4, which is my standard deviation, divided by the square root of n. So s over square root of n is my multiplier. Multiply that by the 1.96. So my interval is going to be basically 412.8 plus or minus roughly 35. So I can do that calculation here and get the lower limit and the upper limit. So my confidence is 95% confidence that the mean of this data will fall between 378 and 447. So that's one way we do the calculation. And also, we're often told, what if before we ran that experiment? Suppose we don't have that data. If someone had said, we think the variance is going to be 114, so we're not being given the 112 over here. We said, we think the variance is 114. How big a sample should I test in order to get a 95% confidence level out of there? So if I want to have 95% confidence that my width will be 45, which is fairly narrow, the width here is twice this interval, so it's 68, 69. So how can I, well, how big a sample of 40 gave me a 69 interval. How big does my sample have to be to only get a 45 interval? So there's the formula that I use for that in your text. To calculate that, I label it as n prime, because that's going to give me a number with a decimal. So since the size of your sample has to be an integer, you simply round that up to 99. So a sample of 40 was good enough to get an interval that was 69 wide. To get a sample that's an interval that's only 45 wide, I would have had to run a sample of 99. So that ability over here to calculate the confidence limits given the data, the ability over here to calculate how big a sample you should run in order to get the results you're looking for is very, very important, because if somebody had wanted a very narrow sample, very narrow range, but ran only 40 samples, they ended up with a range much wider than they expected. So you often have to be able to calculate what's the best sample size to use when I run my experiment. Problem 15, the fifth problem, is a very simple one. It simply says, for any given z, can you translate it into its probability? So it's they're testing our ability to get a z for the probability. At 0z, that's half my curve. If I do maybe a z of 1, I can get 84% of my curve. A z of 2, I get 98% of my curve. A z of 3, I get virtually 100%, largely because I'm not including decimal places here. So if I round that out as I go, 6 sigma would be this number here. If you're dealing with a 6 sigma type of environment, again, I need more decimal places for that. There we go. So that's a pretty big process. So if I do my z of 1.645, that's my 95% confidence interval. If I do my z of any other number, I'm going to be able to get that. So the ability to take your z and come up with the norms dist of that is very, very important as you go through. If you're not using Excel and the functions built into Excel, the capability to calculate these numbers, you could look up 1.6 and then the 0.04 column in the table in the front of your text. And then lastly, the more complicated process says, can we balance out proportional numbers and come up with a confidence bound? I think this problem looks for a lower confidence bound, but with a little changing of the math from a minus to a plus, things of that nature, you can get the upper confidence bound. So out of a sample of 200 with maybe 27 defectives, we can calculate the proportion of defectives to be 13.5%. We use our standard formula to take the square root of n times p times q. To get our standard deviation. So that's our setup here at the top, just numbers that we know. We're told, what might the 99% confidence interval be, confidence bound be? 1 minus the confidence level gives us our alpha. We don't divide by 2 here to take alpha over 2 because the problem is looking for a confidence bound. It's a one-sided test, so we want the entire 1% alpha on one side. But the process is the same. We look up the norms inverse of that, get a 2.326 z factor. And then the equations we use to do that, these equations are more complicated. You have to look at your text on how to do the balancing on page 289. First, you've got to find that median value using a formula that's relatively complicated. And then after that, do the interval calculation for that, and then combine the two into your value. So I won't go through every step of that, but the calculation of these two is fairly important. You need to know how to do that, and it's a little tedious even in Excel, so be careful. But the proposition blue box on page 289 has those formulas that you need. Good luck.